from Michel Brune, who's in Paris, and he's going to tell us about circular Rydberg atoms. Michel, please go ahead.
Okay, thank you for the introduction, and thank you for having organized this remote presentation. I really apologize that I cannot come physically for very silly reason related to Brexit and to the fact that I am not yet used to the new rules, so sorry for that. So I will talk about circular Rydberg atoms for quantum simulation, which is the main project running in our lab in Paris presently. So as a brief introduction, let me just remind you, but you already heard a lot about that trapped Rydberg atoms are very good for building quantum simulators when you consider starting with ground state atoms trapped in optical tweezers and which are transiently excited to Rydberg states where they experience strong dipolar interaction. And you heard about very beautiful experiment performed in the Paluzzo group or in Harvard, where a quantum simulation can be performed by manipulating up to like 256 atoms. So all this is very beautiful, but of course, as everything has some limitations. And one limitation is that in this experiment, the ground state atoms are trapped, but as soon as you excite the Rydberg atoms, you switch off the trap and the atoms start to fly away, which means that after a few tens of microseconds, the atoms are not anymore at the right place and the simulation is gone. This limits, this is the first limit for the simulation time. Another strong limit is the lifetime, the finite lifetime of the Rydberg atoms, which for low angular momentum levels involved in this experiment is in the range of 100 microseconds, which means that if you manipulate 100 atoms at the same time, after 1 microsecond, you already lose one atom. This is a very strong limitation for the timescale of simulation. And if you look at present experiment, timescale is like a few microseconds, corresponding like to about about 10 exchange period of the dipole interaction. So if you switch to circular Rydberg atom, I think the rule of the game is changed, because as soon as you put the atom at cryogenic temperature, the lifetime you can expect is like 30 milliseconds for n equal 50 at 0 Kelvin. And you can even dream of going further by inhibiting spontaneous emission, as we proposed in this physical review paper, where we could expect to have trapped circular atom for lifetime as long as 1 minute. So this corresponds to huge time scale for the time scale of the exchange period and opens the door to very long time scale quantum simulation for exploring, for example, non-equilibrium phenomena or long thermalization time phenomena. So before going into the detail of what we did with the circular atom, like trapping and making them interact, let me remind you a little bit about the basic of the structure of Rydberg multiplicity. So here I have represented the Stark diagram of the n equal 50 multiplicity for rubidium. So one secret for a good manipulation of the circular atoms is to always have some electric field applied to the atom, fixing the quantization axis and somehow isolating the circular state from the rest of the multiplicity. So on this multiplicity, this kind of diamond shape structure, which is very regular, you are at the center with a low value of the magnetic quantum number m, the so-called elliptical states, which align with the dipole parallel or anti-parallel with respect to the electric field, depending whether you are at the bottom or the top of the multiplicity. At the bottom of the multiplicity, you find low angular momentum states, which are very important for that because they are laser accessible. They have good matrix elements for laser excitation. But the limitation is that they also can decay by optical transition and emit optical photon to go back to the ground state. This process limits the lifetime to like 100 microseconds. And if you cool these atoms to cryogenic, if you cool the environment to cryogenic temperature, you cannot expect an improvement better than a factor 2, because you cannot remove the optical transition, which are not sensitive to black body transition. On the other hand, at the end of the diamond, on both sides, you have the circular state. And when you zoom into this structure, you have well isolated circular level, which have only one decay channel. For example, the 50 circular state only decays to the just next to him 49 circular state. This is a microwave transition, and also it have a large dipole, it have a low frequency, which makes its lifetime long, like 30 milliseconds at 0 Kelvin. If temperature is not 10, but 4 Kelvin, the lifetime you expect is 10 milliseconds, which is already a factor 100 improvement with respect to low angular momentum level. If you are operating at room temperature, which is our present case, we are not yet operating the experiment at cryogenic temperature, lifetime become comparable to that of low angular momentum states. So another interesting feature of the stark multiplicity of the hydrogen atom is the facility to navigate within this multiplicity by controlling the atomic state by applying some radio frequency field. So if you apply a sigma plus polarized radio frequency field, you go along this diagonal and you can transfer low angular momentum state into the circular state. If you apply sigma minus polarization, you can do the same, but along the upper diagonal of the system. And indeed, this is a very rich system involving like 2,500 levels, which is a very nice playground for playing quantum simulation, for example, with artificial dimensions, because this set of levels provide like 50 level artificial dimension sublevel. And all the properties of this is contained in the SO4 symmetry of the hydrogen atom. So I will not tell much about that, but let me just say that we perform a very nice navigation along this border of the multiplicity in collaboration with Christian Koch. We developed a quantum control method to have a very fast and optimized circularization from low angular momentum states to circular states, which can be performed in like 100 nanoseconds. So let me now present you the rubidium circular Rydberg atom experiment, which is an atomic tweezer experiment, and whose principal investigator is Clément Servet. So in this experiment, we recently demonstrated the laser trapping of a circular Rydberg state. So what is the principle? The trapping of Rydberg atom relies on ponderomotive trapping. That's basically the force exerted by light, by laser light, on the Rydberg electron, which looks like a free electron when seen by the laser. And basically, when you trap a Rydberg atom, you trap it by exerting a force on its Rydberg electron. One drawback of this kind of trapping is that the Rydberg atoms are low field seeker, so they can only be trapped in the so-called bottle beam trap, which experience a zero of the optical field amplitude at the center of the bottle, and which are closed in 3 dimensions. So in this talk, I will present you the trapping of circular atoms in an array of bottle beam traps. We have indeed an initial array of 18 Gaussian beam traps, which are used to trap the ground state atom and to prepare them deterministically. And then when we circularize the atom, we switch to another array of traps, which is an array of bottle beam trap for trapping the circular atoms. So here is a sketch of the experimental setup, which basically is constructed around this complicated block, which is a piece of sapphire holding many kind of electrodes to apply electric field, radio frequency fields on the atoms, controllable in all directions of space. And the important axis for the tweezer beam is the red axis here, the horizontal red axis, which is the axis along which you find two aspherical lenses which are adjusted to focus the beam at the place of the atoms to prepare to realize the optical tweezers. So outside the ultra high vacuum chamber, we have the usual tools involved in Rydberg atom tweezer experiment, except that here we have to use two different SLM setup, one for preparing the Gaussian beam for trapping the ground state atoms, and one for preparing the bottle beam for trapping the circular atom. In addition, we have an acoustoptic deflector setup in order to be able to rearrange the ground state atom to deterministically prepare the lattice with one atom per side. As everybody, we have also a camera which allows to see the individual atom and allow to discriminate very well between empty sites, which are here on the left, and sites containing one atom shown on the right. So the tweezer light is 820 nanometer. The waist of the tweezers, Gaussian tweezer, is like 1 micrometer. And in this wrapping experiment, we set a large interatomic distance of about 15 micrometer so that the atoms do not interact and are not perturbed by interaction for demonstrating trapping. So here is the timing of the trapping experiment. So we start with Gaussian tweezer. We load them with ground state atoms. And here is the image of randomly loaded initial states in the Gaussian tweezer. Then we image the atoms so that we know where there are atoms in the ground state. We then apply circularization. So we switch off the Gaussian tweezer. We switch on the laser beam exciting the 52D level by a 2-photon optical excitation, which is very standard in this field. Then we apply some microwave transition from 52D state to the 52F circular state. We switch on the electric field and we perform radio frequency adiabatic transfer to the circular state, which is prepared in the presence of electric field, and the circular orbit is perpendicular to the electric field which sets the quantization axis. So as soon as we excite the D level, we switch on the bottle beam and the Rydberg atom is trapped. Then we wait for some time, like duration tau, during which the bottle beams are on and circular atoms are supposed to be trapped. And in order to detect the trapping, we go back to the ground state by decircularizing the Rydberg atom. So we just apply the opposite sequence as the one used for preparation of the circular atoms. And in the end, we take a final picture of atom in the ground state. So if everything was nice, this atom become circularized, trapped, and is here again. And in the end, we count the number of remaining atoms. So we measure the recapture probability, which reflects the probability to have stored the circular atom all along this complex sequence. And here is the result. So we perform two experiments. One experiment without bottle beam, which are the red dots on this curve. And you see that when you don't have the bottle beam, the recapture rate, which is significant at very short delay, drops to 0 very fast, in like 25 microseconds, which is the time needed so that the atom in free flight leave the trapping region of the Gaussian bead at the temperature of 8 microkelvin that we have in this experiment. Then if we switch on the bottle beam, we observe a much lower decay. So the data are the blue curve, with a decay time of about like 125 microseconds. And indeed, this decay time is not related to the trapping time. It's just limited by the blackbody decay of the 52 circular state into the neighboring circular state due to blackbody radiation. So we can model this blackbody radiation very well and model the decay of the circular state very well. And if we do so, the dotted line corresponds to the decay you expect just considering blackbody radiation-induced losses. So it fits very well the data. And to even make it clearer, we represent the same data in logarithmic scale over a longer time scale, which goes up to 5 milliseconds. And you see that without trapping, decay is very fast. With trapping, decay is slower. And now if we normalize the blue data with the dotted line, which is the expected decay from the master equation, you get the green data points, which shows that up to like 1 millisecond of trapping decay is nearly losses and defects of trapping is nearly negligible. And after 1 millisecond, you observe a residual exponential decay with a time scale of the order of 5 milliseconds, which is very difficult to quantify because counting rates are very low in this region and some background signal may perturb the measurement. So this is a clear demonstration of trapping the circular atom in an array of 80 bottle beams. So the second experiment we did with the circular atom is to use the decircularization and recapture technique in order to perform optical detection of microwave spectroscopy. So in this experiment, we have the same array of trapped atom, and we perform microwave-induced Rabi oscillation between the 52 circular and the 50 circular level. So it's a 2-photon transition. And we measure the population of the 52 circular in 2 different ways, either optically by decircularizing the atom after performing the Rabi oscillation during this time, or by the more usual technique of field ionization, which was already discussed this morning, and which basically consists in applying a ramp of electric field on the atom, which successively ionizes the various Rydberg levels involved in the experiment. And the ions produced by this ionization are counted with a channel trend detector. So you see on this ionization signal, the ionization peak of the laser populated 52D level, the 52F level, which is populated by microwave, and then the set of circular states of interest around the 52 circular state that we can populate with various microwave transitions. So you see that there is a very nice selectivity of the ionization detector with respect to the principal quantum number of the circular state. So we now use this 2 methods of detection, either optical or field ionization, to monitor the Rabi oscillation between 52 circular and 50 circular. And here is the signal average over the 18 sites of bottle beam traps. And you see a very nice Rabi oscillation. And the nice thing is that you exactly measure the same thing optically as compared with field ionization, provided you normalize the signal to the initial recapture probability. So in addition, the optical method is spatially selective. So you can look at the individual Rabi oscillation of each of the circular atom trapped in each tweezer. And you see that this allows us, for example, to characterize very precisely the gradient of Rabi frequency of microwave, which is a little bit faster on the left with respect to the right by about 10%. And this is due to the fact that there is some stationary wave in the setup, and the atoms are not placed at exact antinode of this microwave. And this could be improved by moving the microwave source. So another measurement we did is to measure the trapping frequency of the Rydberg atom into the bottle beam trap. And for that, we just prepare the Gaussian tweezer a little bit shifted with respect to the bottle beam tweezer, so that the atoms are trapped initially not at the center of the bottle beam, but a little bit on the side. And we look at its oscillation by looking at recapture probability as a function of the oscillation time. And we look at recapture after a delay of 15 microseconds where bottle beams are trapped. In this case, when the atoms are fast, they just leave the trap in this 15 microseconds, whereas when they are just at the turning point, they don't move and they can be recaptured. So we expect a recapture signal oscillating at twice the frequency of the oscillation of the atom in the trap. And here we very clearly observe a trapping frequency of about 16 kilohertz, which is what we expect for a trapping power of 20 milliwatt per site. And the trapping frequency, you can also check that it is very homogeneous within the set of bottle beam. Here is the color map of the various trapping frequency of the various tweezers. One is pathological and all the others are very similar. So now let me go into the investigation of interaction between the Rydberg atoms. And we first start by investigating a two-body dipole-dipole interaction. So in this experiment, we prepare pairs of atoms in the ground state, so that the black dots here. So we prepare 3 pairs of ground state atoms, and we prepare them deterministically by using the rearranging beam, so that there are exactly 3 pairs of ground state atoms at the beginning. Then we perform circularization, and first we choose the orientation of the inter-atomic axis at a precise angle of 54.7 degrees, which ensures that interactions between dipole-dipole interactions between the 2 Rydberg states are negligible during the circularization, which involves large levels with large dipoles, which may interact. We prevent them from interacting by this choice of this angle. Then for a pair of atoms prepared in 52C, 52C, the microwave, we perform a 1 photon microwave transition to the 51C. So in the absence of interaction, you can first emit a photon, go to 52C, 51C, and then emit a second photon to go to 2 atoms in 51C. In the presence of interaction, this does not work anymore because you know that there is a splitting between symmetric and anti-symmetric superposition of the 2 levels, which are directly coupled by the dipole-dipole interaction. And you expect an energy shift proportional to the dipole-dipole coupling strength, which scales up 1 over the distance cube, and with this angular dependence, which is very classical for dipole interaction. So we now perform the microwave spectroscopy, and we monitor the spectrum of excitation of 51C circular atom as a function of the distance between the 2 atoms. So for each distance, we prepare a different set of bottle beam trap with a different distance. So you see the family of spectra, which demonstrate the expected splitting. So why are there 2 components? Indeed, here is a line which is not moving and which corresponds to a 2 photon transition between the 2 atoms in 52 circular to 2 atoms in 51 circular states. And this line does not move significantly when we change the interatomic distance. And the second line is the excitation of the plus state, and it is shifted to the right on this spectrum. So we can fit all this data and represent the shift, the dipole-dipole shift as a function of the distance in logarithmic scale. You see that it's very well, except for the maybe last point, fitted by a straight line. And if you just compare the data with the ab initio theory, you get the red line, which becomes the green line if you correct just the magnification of the optical system. Indeed, controlling the distance depends on the calibration of the magnification of the optical system and on the precise knowledge of the focal length of the aspherical length. And I think it's reasonable that we estimate this with a precision of 2.3%. So here we have an excellent agreement with the theory, and we really control very well the dipole-dipole interactions between the pair of atoms. Now we can do similar measurements at a fixed distance of 13 micrometer, but varying the angle between the electric field and the interatomic axis, which amount to vary the orientation of the circular orbit with respect to the electric field. And we expect theoretically again the 3 cosine square minus 1 variation, which is very well fitting the data if we take into account the same correction of magnification factor as compared to the measurement as a function of distance. So you see that when the electric field is aligned along the interatomic axis, the interaction is maximum and is attractive, and it becomes repulsive and factor 2 weaker when we go to the electric field perpendicular to the interatomic axis. So finally, we also demonstrated the effect of the interaction during the preparation of circularization. So what is the effect? The point is that once you prepare the low angular momentum states, here at the border of Stark multiplicity, you prepare a non-circular state with maximum value of the dipole. The dipole can attract or repel each other depending on their relative orientation with respect to the quantization axis. So in this experiment, instead of exciting the atoms with an angle 54.7 degrees with respect to quantization axis, we vary the orientation of the dotted line so that intentionally we have interaction during circularization, which induce some motion. And then we measure this motion by the microwave spectroscopy I have just discussed. When the distance is varying because the atoms are oscillating, the dipole-dipole shift is also oscillating, and we can deduce the distance between the atom like that. So you see that for maximum interaction between the dipole at 0 degree, we see a large amplitude of oscillation induced during circularization, which change phases when we switch to 90 degree because the interaction becomes repulsive instead of attractive. And if we go to the magic angle, then the oscillation is nearly invisible. It's the residual fitted amplitude is like smaller than 50 nanometer and could be related to relative misalignment of the trap at the initial time of the experiment. The oscillation frequency we observe is the one we expect for the power we had in the bottle beam in this experiment. So what next in this experiment? I think now we are ready to have up to like 20 trapped circular atoms to perform first quantum simulations, not with only 2 atoms, but with 20. The present limit on the number of atoms is the trapping power of the laser that we have presently. We use 20 milliwatts per bottle beam trap. And the main other limitation is that we operate at room temperature, which means that the lifetime of circular atom is not much longer than the lifetime of low angular momentum atom, which means that the real next step is to switch to cryogenic setup in order to really benefit from the long lifetime of the circular levels. So now I will switch to a second experimental project that we constructed, which is more long-term project, but which consists in switching from alkali to rare earth atoms, let's say to strontium atoms. So why are 2 electrons atoms interesting for quantum simulation? You already heard about the merit of strontium in the talk of Manuel Andres. But for circular atoms, this interest is even stronger. And the point is that circular Rydberg atoms are very nice for quantum simulations. But once you are in circular level, you do not have any more easy optical way to manipulate the atom, because you basically have no optical transition from the circular state to other levels. So it means that selective detection of circular atom is difficult, and what we needed to do is to decircularize before detecting the atom. And local addressing of the circular atom cannot be done optically, which is also a limitation. Of course, with the rare race, it's a game changing, because you have a second electron, which is the electron of an ionic strontium atom, that you can optically manipulate with some metastable levels, with some all tools that you can imagine that can be used for manipulating the ionic state together with the circular state outside the atom. And the very important property of the circular atom, which makes them interesting with this respect, is that they basically are expected not to auto-ionize, because the circular electron is so far away from the atomic core that you expect negligible auto-ionization, in very strong contrast with the case of low angular momentum level, which usually auto-ionizes on a very short time scale, like picoseconds or hundreds of picoseconds, as soon as you start exciting the core, for example, in the 5p level. So this experiment is driven by Sébastien Glaise, and so he's playing the game of putting together the merit of the circular atom of strontium together with the properties, optical properties of the strontium ion. So in the first experiment, Sébastien demonstrated laser cooling of an atomic beam of strontium circular atom by using the radiation pressure exerted on the ionic core on the 5s1/2 to 5p3/2 transition, addition using some repumping. So basically, this is an atomic beam experiment. The atoms are flying from left to right. They are circularized at the center of the structure. And once in the circular state, we send a resonant blue beam and the repumping beam counter-propagating with respect to the atomic beam. Then we measure the arrival time of the atom, of the circular atom, by using the ionic detection, the field ionization detection method. And you see that as a function of the duration of the cooling pulse, so this is duration of the blue laser pulse, you see some narrow distribution of the atoms because we select the velocity at the level of excitation, and the propagation of this packet of atoms shows the slowing down, because now, as a function of cooling laser direction, the atoms, the circular atoms, arrive later and later. So we can analyze this signal in order to measure the velocity of the atom as a function of pulse duration. And you see that the velocity sense in the range of several tenths of meter per second for interaction time of like 100 microseconds. So this is very efficient, and this is promising for providing a way for cooling the Rydberg atom once it is in the circular state. And if you have in mind to perform quantum simulation on a long time scale, it becomes important to control the atomic motion, which could be heated by parametric heating or any kind of parasitic source of heating. So in addition, we demonstrated that the circular atom is so weakly sensitive to what happened in the ionic core that even if you prepare a quantum superposition of two circular states, you can preserve the coherence of the superposition that you can measure in the Ramsey fringes experiment on the 51 circular to 49 circular levels. And that basically, once the atoms scatter like 2000 photons, the reduction of visibility of the fringes is nearly negligible, which is also very promising for the use of this cooling tool in quantum simulation. So another experiment, and I will finish with that, is a demonstration of residual weak interaction between the strontium ionic core and the circular atom. And this interaction is of electrostatic origin. Indeed, it's the quadrupole of the ionic core when prepared in the 4D metastable state, which couples weakly to the electronic distribution of the circular level. And this results in the splitting of the sublevel of the 4D 3/2 metastable state of the ion by an amount which depends on which circular state is populated. The larger the principal quantum number of the circular state, the weaker the interaction. So it means that this coupling, this shift, allow you in principle to measure which is the principal quantum number of the Rydberg level. So we characterize this shift in two experiments. First, we perform a microwave spectroscopy experiment. We induce a 2-photon transition between 51 circular and 49 circular level. And we perform it for two different core states of the ion, either the ion in the 5s level, which basically does not interact with the circular level, or in the 4D level with the quadrupole, which produces a splitting of all of these circular levels. And then the microwave spectroscopy is a single line if the core is in the 5s, that's the black dots here, and it becomes splitted with two components with a very well-defined value of mg. The mg equal 1/2 is shifted to higher frequency, and the 3/2 is shifted to the lower frequency. So you see here that with a microwave spectroscopy, you can observe whether the core is in the 5s or 4D level. And that's the way to measure with the Rydberg atom what is the optical properties of the core. Of course, you can do the opposite game and look at the core in order to identify in which circular state you are. So that's what we did in the second experiment, where we perform Raman spectroscopy between the Zeeman sublevels with a pair of laser beam, which are close to resonance to the 4D to 5P transition. So if we prepare the circular level in the 51 circular state, we get the Raman spectrum with one line, which is narrow and peaked, and at this frequency. Now, if with the microwave pulse we prepare the Rydberg atom in the 49 circular state, we observe a larger splitting of the line and a larger shift of the Raman spectrum. And you see that if you set your Raman laser at this frequency, depending whether you have a low transfer or a high transfer, you can know whether the atom is in the 51 or 49 circular state. So that's a way to encode the number, the principal quantum number of the circular state into the ionic core state. So again, we check that this can also be done for manipulating a coherent superposition of two circular states. And basically, in this experiment, we perform Ramsey spectroscopy on the 51 circular to 49 circular transition, microwave transition, and we add on one arm of the interferometer a Raman 2-pi pulse, which occurs only if the atom is in the 49 circular transition. So this is this Raman pulse here, and we observe a shift of the Ramsey fringes by pi related to this 2-pi pulse, which is the basic ingredient for performing the quantum gate coupling the ionic core to the circular level 51 and 49 states. So let me now conclude. The rubidium experiment demonstrated the trapping of the circular atom. We observed the two-atom dipole-dipole interaction. And on the short terms, we are now ready for performing quantum simulation with up to like 20 trapped circular atoms. And we have to switch to cryogenic environment to go further away. For strontium, the experiment is up to now an atomic beam experiment in which we demonstrated laser cooling, slowing of the atom, and we demonstrated manipulation of the atomic core using the quadrupole interaction between the circular states and the ionic core state. And now we have a very nice system, kind of hybrid system, putting together the merit of trapped ion physics for quantum simulation and of Rydberg atoms for quantum simulation. And to go further, we are now building a cold atom setup experiment, and we try to build it directly in cryogenic environment to develop further this experiment at the level of single trapped atom. So I thank you for your attention.
Thank you very much, Michel. So we have some questions. Yes,
so could you foresee doing readout with atoms in low L states and then doing operations with the circular states?
So you mean which readout you mean?
So having arrays that are mixtures of low L atoms and circular atoms.
So you mean during the you mean during circular rotation, we may have both low L and circular atoms, and we could, you mean how we can selectively detect the one or the other?
No, I meant sort of kind of like a two species kind of arrangement where some of the
Okay.
atoms would be low L and some would be circular.
Okay, so you can imagine a mixture of two different atoms, so that you have the circular and you use another species for, you have in mind to use another species to measure the circular atom with low angular momentum level. So I think this could be done. It's technically challenging because you have to mix two different species, but in principle it should work.
Any additional questions? I had one question actually about the interactions. So you had a plot which showed the interaction as a function of distance, and the curves, that one, yeah, this one. Yeah, so the curves are also broadened. And I guess the broadening tells you about the spatial distribution of the atom inside the trap. Did you try to fit that?
Okay, so indeed, presently the broadening is there only for a very silly technical reason. Data acquisition is kind of very long for this experiment. And so the students have to program a sequence of data acquisition which runs all over the night. And to have the same time spent on each spectra, they have the same number, about the same number of measurement points, and then they decrease the duration of the microwave pulse when the splitting is increasing. So that here it's kind of artificial broadening related to finite duration of the microwave pulse. Okay. Of course, if we do this spectrum with longer pulse, we start seeing some broadening, but I think it's not visible on the spectrum. The spectra are related really to the duration of the microwave pulse, which is unfortunately not fixed when we decrease the distance.
Okay, thanks. Yeah, Frederick.
Do you see differences when you go to the maximal m, so m equal n minus 1, or the negative of this one? When you look at the quadrupole interaction, for instance.
So we cannot change the sign of m because basically when we circularize, we always go on the same side, which is determined by the. So here, basically for low m level, we prepare always a given side, which is determined by the polarization of the atom and the optical pumping and the orientation of the magnetic field. And so we could go the other way, but it consists in basically reversing the magnetic field, and we do not expect that it changes anything to the interaction. But in the experiment, we always prepare the circular state on the same side.
Thank you.
Okay, so I think we thank Michel for a very nice talk. Thanks very much.
Thank you.